Okay, now that we have vector components, we can now go back to our laws of dynamics, Newton's laws, particularly the first and the second. And we're going to write them in component form. So it's really not that complicated. All that we're going to do is deal with everything in the x direction or the y direction independently. And so if we rewrite, this would be in the x direction. So we can see that in the x direction, Newton's first law says if the net force in the x direction is equal to 0, then the acceleration in the x is equal to 0. And this is if and only if. His second law says, well, the acceleration in the x direction would be the net force in the x direction divided by mass. So you see it's the same thing. We're just adding in these little components. And so we'll just deal in the x direction or in the y direction. So we get the same thing in the y. Net force in the y is 0 means the acceleration is 0, and the acceleration in the y would be the net force in the y divided by the mass. So let's apply it, and then you can get a feel for how this works. Just keep in mind, you could use, in one case you might use Newton's second law in the y and his first law in the x, or vice versa, and that's what we'll see here. And so we have basically you're pushing against a book, but the book is sliding. So we probably have some acceleration down. So the book is sliding. You're pushing against it with a 21 Newton force angled at 45 degrees. That's against the horizontal. The mass of the book is 2 kilograms. Find the normal force and the acceleration in the y direction. Okay, so first let's think about the forces. And so our system is going to be the book. And so I'm going to draw it down here. So here's the book. I'll go ahead and put the 2 kilograms inside of it. That's typically what I do. And then your hand is pushing on it. Now, we always draw forces as pulls. So even though I'm pushing it this way, it's coming out the other side like this. And this is 45 degrees. And we'll call that the force of, say, the hand. Okay. And then gravity is also acting on this thing, so that's pulling it down. So we have the force of gravity. And to calculate the force of gravity, that's always m times g. Okay, but it's against a solid surface, it's sideways, so the normal force actually comes out in this direction. So normal force is this way. And that should be horizontal. I drew it. It's a little bit, looks like an angle, but it's actually straight out of the wall. Okay, so to find the normal force, basically what we're doing is the normal force is going to be all in the x direction. We're using just a standard coordinate system here, so x and y. And so I need to add in some components. I'll do my components in red. This one is all in the y direction, and this one's all in the x direction. So it's just this one that we have to break into components. So I'm going to get this component here. This will be my force H in the x direction, and then I'll get the force H in the y direction. Okay, so there's a force diagram. One note on the AP exam, do not put components on a force diagram. So you only draw the forces, not the components. These are not forces, these are pieces of that force. Okay, let's see. I'm going to do my normal force. So first we're going to find the normal force. And for this, we're going to be dealing in the x direction. Okay. So thinking about the x direction, the book is not moving in the x direction. So we know the net force in the x direction is equal to 0. So looking at my x direction, I have this positive force of the hand in the x direction minus the normal force, which is in the x direction, is equal to 0. So the normal force is going to be equal, I moved this over, but I'm flipping the whole equation around, the force of the hand in the x direction. So using Newton's first law, we get to this. The normal is going to be this one. And we can kind of see that. They should balance out. I didn't draw these properly. This one looks longer, but these are actually the same. And then using some trig, the normal force is going to be, it's the FH in the x direction is next to the angle, and I know this force, the hypotenuse, so that's going to be cosine. So we end up with force times cosine 45. degrees. So the normal force is going to be the force, 21 newtons, times cosine 45. And then if we calculate that, we get a normal force of 14.85 newtons. And that would be in the negative direction. So we're coming back this direction. The reason that I added it on down here is because I included the negative up here. And so that makes everything positive. So this is magnitude. If you truly just add, then it creates a negative. But again, I know it's going left, so I know it has to be negative. All right, let's do the acceleration in the y direction. So now to get the acceleration in the y direction, I'm going to work with Newton's second law. So his second law says the acceleration in the y direction would be the net force in the y direction divided by the mass. So the acceleration in the y, let's add up all the forces in the y direction. So I have this one up here, and that one's positive, minus the force of gravity divided by the mass. Okay, so the acceleration in the y. The force of this one is going to be, this is the opposite, and I know the hypotenuse, so this would be F sine theta. So over here I get F sine theta minus the force of gravity, which is mg over m. So my acceleration in the y, now we can substitute. The force is 21 newtons, that's given. So 21 sine 45 minus the mass, which is 2, times 9.8. Notice I don't put a negative on the g because I already put the negative on the force, divided by the mass, 2. And so calculating that, you get an acceleration in the y direction of, I got negative 2.38-ish meters per second squared. That makes sense. I should have negative. It's coming down. It's a bigger force, so it's accelerating downward. So here we applied Newton's first law, and then we applied his second law in the y direction. But this is basically it. So same kind of stuff we've been doing. It's just that we may have to do stuff twice. All right, let's try another example. Okay, so let's suppose you're pushing a, 10 kilogram box across a surface which has friction. And let's say the coefficient of kinetic friction, let's make it 0.2. And you're pushing with a force of, let's say 30 newtons at, let's just do, let's do 40 degrees. So you're pushing this box across the floor. It has some friction, so we want to know what's the acceleration of the box. So the acceleration in the x direction. Okay, to do that, the first thing we're going to do is you need to draw a force diagram. So let's draw a force diagram for the box. So I'll write my 10 kilograms in here. And now we got to think of all the forces. So I'm pushing down, but we draw it out the other side. So it's as if I'm pulling this way. And then this force is going to be 30 newtons. We'll call that the force of the, push. Okay, but there's friction. I'm pushing this direction, so the friction acts backwards. So we're going to have some kinetic friction coming back. Kinetic friction. Okay, and then we have gravity, so gravity is pulling it down. And we calculate the force of gravity or weight using mg. And then it's on a solid surface, so we have a normal force pushing up. All right, that's it. Those are all of our forces. Now we want to find the acceleration of the box. Okay, so let's work in the x direction. We're going to work in the x direction. And in the x direction, we assume there's some acceleration because that's what they're asking for. So the acceleration in the x would be the net force in the x direction divided by the mass. So acceleration in the x, let's list all the forces in the x direction. Well, I got a piece here of the friction, so we're going to have this right here. So this would be my force in the x direction, and that's at 40 degrees. So since it's next to it, it's going to be cosine. So it'd be force cosine theta, and then minus the kinetic friction. All of that divided by the mass. All right. Remember friction, that's the coefficient times the normal force. So we got to figure out the normal force. So what I'm going to do is I'm going to work now in the y direction, so I can figure out the normal force, y direction. Okay, in the y direction, it's not accelerating, so I know the net force in the y direction is equal to 0. Adding up all the forces in the y direction, I have the normal force. I have the negative of the force of gravity. But I also have this piece right here. So I also have some force in the y direction here. And since it's across from the angle, that's sine. So it's going to be force sine theta is equal to 0. So notice in this case, my normal is not going to be equal to my force of gravity. So you got to be careful with that. And it kind of makes sense. You're kind of, if you're pushing down on the box, you're kind of pushing it into the floor. So the floor is going to push back harder. So the normal is bigger than as if this thing were sitting at rest. So solving this, we can get the normal is going to be equal to the force of gravity plus F sine theta. All right, at this point we can go ahead and calculate it to get the normal force, and then we would substitute back in. Let me substitute here. So we're going to substitute this into here. So we get the acceleration in the x direction. It's going to be F cosine theta minus the coefficient times the normal force over the mass. All I did was substitute the friction is coefficient times the normal. Oh, that's kinetic, which they give me up here. Or I gave you. All right, two ways of approaching this. I can take all of this and plug it in and deal with it, or I can just calculate this now. Let me go ahead and substitute real quick. So the normal force of gravity is mg plus F sine theta. Okay, at this point you can just plug in some numbers and get a value, and then take that value and plug it in, and then plug in all your numbers. I'm going to go ahead and do the substitution so you can see what it looks like. So the acceleration in the x direction is going to be F cosine theta minus the coefficient of kinetic friction times the normal force. And I got to put it in parentheses because I'm adding over here. So I get mg plus F sine theta. All of that divided by the mass. Now I can plug everything in. Let me scroll back up so I can get my values. Oh, they're right over here. So we get the acceleration in the x is going to be the force 30 cosine 40 minus the 0.2, the coefficient, times the mass, which was, I think it was 10, times 9.8, plus the force 30 times sine 40. And we're going to divide all of that by 10. Now we're going to plug everything in. So I'm going to put it all in my calculator. All right, so I made up bad numbers because the acceleration in this case is negative. So we get a negative like 0.48 meters per second squared. But this wouldn't be the case because the frictional force, let's think about that. Let's go back up here. So the acceleration, what we got was in this direction. However, the only force acting this way is kinetic friction, and kinetic friction only comes from opposes motion. So that's a result of pushing forward. Point is, I made up these numbers, so it didn't work out. We would have to increase the force, so this is not possible. We would have to increase this force to actually get some acceleration in this direction. But the idea is there, so it's more in the algebra rather than that final answer. I think we'll do one more. Okay, so here's the deal. You're pulling a couple of kids on a sled across snow. You're exerting a 100 Newton force on a rope angled at 37 degrees above the horizontal. The question is, how fast is it going after it's gone 10 meters? So let's start with a force diagram. So our force diagram, our object of interest is going to be the kids on the sled. So it's all of this stuff, which is what they tell us, 60 kilograms. So I'll put a 60 in here. And then we have the force of gravity acting on them. And then we have the tension in the rope, which they say is equal to 100 newtons. It's on snow, so we assume there's no friction. And then we have a normal force coming up. And I drew this purposefully smaller than this one. Can you see why? I hope so. Okay, and then we're going to assume that the kids, they start at rest. So we'll put V naught at 0 and X naught at 0. And then we want to know after they go 10 meters, so X final is 10, what's their velocity, their final velocity? So they move along in this direction. All right, so what we're going to need is, since it starts at rest and it achieves some some velocity, it's going to have acceleration. And we have distance, so we don't have time. So let's go ahead and get a quick kinematic. So my final velocity squared is going to be the initial velocity squared plus 2a times x minus x naught. And I made everything in the x because we're moving in the x. If this was in the y, I could do it in the y. So this one is 0, the initial velocity is 0, and the initial position is 0. So we get Vf is going to be the square root of 2ax. So we need to figure out what that acceleration is in the x, that's in the x direction. All right, so we're going to have to figure out the acceleration in the x direction. So let's go ahead and try it. We'll try to work in the x. Sometimes it works, sometimes it doesn't. Sometimes we'll have to go to y to figure something out. But we're dealing in the x direction. So basically we have some acceleration in the x, so Newton's second law. And that would be the net force in the x direction divided by the mass. So the acceleration in x is going to be, well, let's see, the only force acting this way is going to be this. The tension in the x direction, and that's my theta. So since it's next to the angle, it's going to be, here I'm going to put tension in the x divided by mass. Now we'll substitute. So my acceleration in the x is going to be 100 times cosine, since it's next to cosine 37 divided by the mass of all the kids, so 60. All right, now we can just plug that in the calculator. And we get an acceleration in the x direction of 1.33 meters per second squared. Now we'll use this up here. So my final velocity would be the square root of 2 times 1.33 times how far they went, 10 meters. And plugging that in, you get a final velocity of 5.16 meters per second. So we didn't even have to go into the y. Now if there was friction, we would have. If I had some friction coming back, I'd have to go into y because I would need that normal force. But that's about it. So there you go.